Hi, my name is Nicholas Dwork. Today I'm going to be discussing non-rectangular field of views, a novel method for accelerating MRI, and this is work that I've been doing with Erin England. With clinical MRI, a localizer scan is initially collected to confirm patient position. The person controlling the MRI, perhaps the technologist, then selects a field of view. Currently, the field of view must be a rectangle, and it must encompass the entire patient. From this field of view and the desired resolution, the sampling pattern is created. The distance between samples is directly related to the size of the field of view in order to satisfy the Shannon-Nyquist sampling theorem. The issue is that human bodies are not rectangular. Thus, there is necessarily empty space included in the field of view. But what if we permitted a non-rectangular field of view, like the blue contour shown here? The area that we'd like to image is dramatically reduced. Can we reduce the number of samples required for a high-quality image? The answer is yes, and that's what we'll be discussing today. So let's say this is a slice of the patient that we want to image. The dark blue contour is the non-rectangular field of view. And perhaps the black rectangle shown here would be the rectangular field of view selected by the person controlling the MRI machine. This would dictate a Cartesian sampling pattern as so. But what if we were to eliminate every other column of these samples? That would cause aliasing. It would replicate the slice of the anatomy and shift it by half. Now, much of the anatomy here is corrupted because of the overlap. But what I'd like you to notice is that some of the image is uncorrupted. We can identify the uncorrupted regions using the field of view provided simply by shifting the contour and looking where it intersects. These dashed lines are horizontal lines through the intersection points. The regions outside of these dashed points do not have any overlap. We can eliminate the inner region. We can zero out any of the image outside of the selected non-rectangular field of view. And what's left is uncorrupted. The question remains, how do we fill in the rest? Well, we know that the total image is the inner portion plus the outer portion. We can take the DFT of both sides of this equation, and equality holds. The DFT is linear, so we can distribute across the sum. And recall that we know I outer. We were able to reconstruct I outer just from every other column of samples. Thus, the DFT of the inner portion is just equal to the DFT of the total image minus the DFT of the outer region. Notice that the inner region has a reduced vertical extent when compared to the total field of view. And this is what we're going to leverage to reduce the number of samples. This is the sampling pattern that we're going to use to reconstruct the image. From the gray samples, we get the outer region. From the addition of the blue points, we'll get the inner region. Due to the reduced vertical extent, we'll be able to separate out the blue points more than we were able to the gray points. And this will be how we reconstruct the inner portion of the image. Okay, I'm going to take the inverse DFT of both sides. And this will ultimately be our reconstruction algorithm. We start out with the outer image. We take its DFT. We subtract that from all of the data that we've collected. And then we take the inverse DFT to generate the inner portion of the image. Let's see how this works. We're going to go through an example of a sagittal slice of an ankle. And the field of view that we're going to use is this L region. The upper right quadrant will be excluded from the field of view. This non-rectangular field of view, this L region, corresponds to a sampling pattern where we collect every other row and every other column. And if we look at any block of 4 samples, we see that 1 is eliminated. We're only collecting 3 out of every 4 samples required for a fully sampled reconstruction. And so this is a 25% reduction in the number of samples. So this is the sampling pattern of the data that we collected. And this is what happens if we do a zero-field reconstruction. There's significant aliasing and the image is highly corrupted. We're now going to show you that the proposed method works much better. Firstly, we reconstruct the image using only every other row. This is the aliasing present. The image has been shifted horizontally by half a field of view and then added to itself. Then we isolate the outer region. And for this image, the outer region is the top half of the image. Once the outer region is isolated, we multiply by the support. This is the support, of course, so multiplying by the support eliminates the upper right-hand quadrant, and here we have an accurate reconstruction of the leg. We're going to take this image, compute its DFT, and subtract those values from those of the sampling pattern to reveal the Fourier values of the inner region of the image. We're then going to compute the inverse DFT of those values to reconstruct the inner region, this time with aliasing in the vertical direction. We're going to isolate just the inner region. That leaves us with the bottom half of this ankle. Summing together these two portions yields the full image. When compared to the zero-field reconstruction, we see the quality is much higher, and we see that the reconstruction with the non-rectangular field of view is very similar to the fully sampled reconstruction. Here are results for several slices of a brain, comparing the fully sampled reconstruction to those of the non-rectangular field of view. Again, the images are very similar. And here's a slice of a pineapple, this time with prospective undersampling, and we see again that the reconstructions are extremely similar. Some final thoughts. This can be combined with standard MRI acceleration methods like parallel imaging, compressed sensing, and partial Fourier sampling. Rather than subsampling a Cartesian grid, you can subsample the proposed sampling pattern. This can also be combined with non-Cartesian sampling. Rather than interpolating onto our Cartesian grid, you would interpolate onto the sampling pattern dictated by the proposed algorithm. And finally, this can be combined with a physics-based deep learning algorithm, where you would incorporate the processing for the non-rectangular field of view into the system matrix of an unrolled deep learning algorithm. A final note, we have applied for a patent on this technology, and thank you for your attention.